If you want reliable underwater communications, stop asking which modem has the highest bitrate. Ask which mix of channels keeps mission control intact even when the ocean changes. Seawater punishes conventional radio. That single fact is why acoustics still dominate most non-tethered subsea links as of 2026. Sound travels far enough at power levels and transducer sizes that real vehicles can carry. But the trade is brutal. The acoustic channel is never a clean pipe. It is a shifting, echo-filled space shaped by the surface, the seabed, and the water's layered structure. Environment matters more underwater than many planners expect. Shallow water can be the hardest case. You get strong surface reflections, bottom interactions, and reverberation that smear signals across time. At a thermocline, and the path can bend in ways that break simple planning. Local noise, including your own platform noise, becomes part of the link budget. So capacity, delay spread, and modem settings end up being site and mission specific. Then there is Doppler. An underwater Doppler is not a footnote. Motion-driven Doppler spread can dominate the entire design for moving platforms. It hits synchronization, tracking, waveform choice, equalization, and packet timing. If an AUV is maneuvering, if currents are moving water masses, or if both nodes are in motion, Doppler can be the difference between a stable link and a silent one. This was identified decades ago, and the message still holds. If you do not test under realistic motion, you do not know your performance. A second counterintuitive point is that underwater communication is not one wireless category. It is a mode-switching architecture problem. Acoustics are the range and robustness layer. Optical links can be a local, high-rate burst layer, but only when conditions cooperate. Magnetic induction and near-field coupling can serve very short-range, sealed interface needs. And when you can dock mate or physically connect, wet mate connectors, tethers, copper, and fiber give you deterministic behavior. Optical is the tempting one, because it can deliver high throughput at short range. Yet the ocean makes optical links fragile. Water clarity, scattering, turbidity, and turbulence all matter. Pointing and alignment matter too, because many optical links effectively demand line of sight. A slight yaw or a drifting platform can drop the link. That is why link repair and fast reacquisition are not extras. They are the product. A practical pattern is to use acoustics for control and safety, then use optical only when nodes are close and aligned. Buffer locally, burst when you can, and fall back cleanly when you cannot. Wideband acoustics add another layer of nuance. Recent work treats wideband as its own regime, not something you can reduce to narrowband assumptions. More bandwidth can mean more data, but it can also mean more exposure to frequency-dependent absorption, more sensitivity to time variation, and more receiver complexity. The real question is not whether wideband is faster. It is whether it beats robust narrowband signaling after you account for motion, ambient noise, power limits, and nonstationarity. Measurement discipline is the third big takeaway, especially in shallow water. Shallow water channels vary with the site, and that has direct implications for procurement and acceptance testing. A lab-demonstrated bitrate is not an operational specification. If you are deploying in shallow water, assume you need site-relevant measurements before you can trust command, telemetry, or safety-critical coordination. All of this shifts attention away from peak throughput and toward mission continuity under intermittency. The frontiers is reliable transfer of data, timing, and command authority through seawater and across pressure boundaries, despite multipath and distortion. That includes interfaces that are not open water links at all. Pressure housings, seals, connector reliability, corrosion, and biofouling can become the limiting factors. And for magnetic induction and through-hull or wired transfer, the published record often lacks clean, quantitative baselines. That is not a reason to ignore them. It is a reason to treat them as a validation gap and fund the testing. There is also a governance lesson hiding inside the physics. Underwater links can carry very different kinds of authority. Telemetry is one thing. Navigation support is another. Vehicle command, habitat authority, and emergency abort authority are in a different class. The architecture must assume outages. Local autonomy has to absorb routine loss of contact, and the system must define timeouts, abort thresholds, and safe states. So the practical strategy is to build hybrid testbeds, not just by devices. Evaluate acoustic, optical, near-field, and through-hull interfaces under representative motion, turbidity, shallow water multipath, and pressure boundary constraints. Separate the control plane from the data plane.